In this video, we're going to go through our different types of radiation, covering a little bit of the history along with our different sources of radiation. So to start with the history of radiation, the history of radiation basically begins in 1896 with the work by Henry Becquerel. He noticed in his lab, in his work with different elements, that there was discoloration of exposed materials when they were exposed to certain types of elements. This work was done along with Marie Curie, who you may recognize her name. She becomes one of the big players in the history of radioactivity and radiation. In 1898, she officially discovered the two elements polonium and radium, and she coined the term radioactivity. In 1903, she wins the Nobel Prize along with Henry Becquerel and her husband, Pierre Curie, for their work, the Nobel Prize specifically in physics for their work in radioactivity. Later in 1911, she on her own won the Nobel Prize in chemistry for the discovery of polonium and radium. Her papers that she was working with, her notes, her lab notebooks, things that she worked with in the lab are still radioactive today, and so they have to be kept in lead-lined boxes. Radium, as the element, was seen as a very, very useful material, and it has kind of a dark history to it. It was used as a medication for a lot of different things. It was used in watch faces. If you're interested in kind of the social, political intersection with science and kind of how some things developed, The Radium Girls is a really fascinating book that goes into the details of government cover-ups and business cover-ups of some of the dangers of working with these materials. And then one of the most commonly associated projects with radioactivity and radioactive elements is the Manhattan Project and the work on the atomic bomb and other types of nuclear weapons. So there's a lot of good things that come along with radiation. There's also some bad things, just like a lot of discoveries in science. So let's look at some of the definitions for radiation and radioactivity. So radiation is the emission of particles or energy. So that's the generic term for any time an atom emits any sort of particles or energy. It's considered radiation. Radioactivity is the process of emitting nuclear radiation. So they're similar, they're related. Radiation is when the particles are emitted, radioactivity is the process that it goes through. One of the terms that we see along with radiation and radioactivity a lot is half-life. And half-life is the time required for half of a radioactive sample to decay into a stable isotope. So last semester we talked about isotopes and how they can be the same element but have different masses. Some isotopes are very unstable, and so they're going to go through what is considered radioactive decay. And so half-life is literally just the amount of time it takes for half of the sample to decay into a different isotope. Things with we have some elements that have very short half-lives, we have other things that have very long half-lives. One of the processes you might be familiar with from biology is carbon dating. Carbon dating relies on the half-life of different isotopes of carbon, which has a very long half-life and can therefore be used to date objects or use it to backwards calculate the date or age of different objects. So there's three main different types of decay when we talk about radioactive decay or radiation. The first is alpha decay. Alpha decay is when a nucleus emits what is essentially a helium nucleus. So a helium nucleus has 2 protons and 2 neutrons. So anytime a nucleus of a different element emits 2 protons and 2 neutrons, it's considered alpha decay. The second type of decay is beta decay. This one's a little bit more complex. During beta decay, a neutron is going to turn into a proton and emit an electron. So the electron's what's leaving the nucleus. However, there's something that's happening before that. A proton's turning into a neutron. So if we compare these two, alpha versus beta, in alpha decay, an element is going to completely change the type of element as well as the mass. Since it's losing 2 protons, during alpha decay, it's going to turn into an entirely different element. and losing 2 protons and 2 neutrons is going to change its mass by a total of 4. In beta decay, that type of element is going to change because a neutron turns into a proton. So your number of protons is going to go up, but your mass is not going to change because the total number of particles in your nucleus is staying the same. So the mass is the neutrons and the protons together. So since that total is staying the same, your mass won't change. And since electrons don't contribute to the mass, that's negligible when it leaves. The last type of decay is gamma decay. And gamma decay is when a nucleus releases a high energy light wave that's called a photon. Gamma decay, for those of you who are interested in superheroes and comics, is probably what you most likely associate with genetic mutations of superheroes, and most commonly the Hulk was exposed to gamma decay in that series. So when we look at their penetrating powers, it's all based on how big these particles are. Alpha decay being alpha particles being the biggest are blocked by relatively simple things. A piece of paper can block alpha decay or block alpha particles. Beta particles or beta decay, since it's an electron, it's smaller, it can go through materials like paper, so it takes something a little bit heftier in order to block beta particles or prevent beta decay. So aluminum is a common one. Gamma decay or gamma particles need a lot stronger material in order to block them. So that's where you'll see materials like lead being used. This is why when you go to the dentist and get x-rays, they're going to put that lead vest on you. Or if you go to get an x-ray on some other part of your body, they're going to cover the areas that don't want to be exposed to that radiation with lead, because lead is very good at shielding from radiation. So there's lots of different sources of radiation that we encounter on a fairly regular basis, and that's considered background radiation. So background radiation comes from naturally occurring radioactive material, and that is something that everybody encounters on a fairly regular basis. The one that's the most common is the sun, and that emits a type of radiation that we call cosmic radiation. So pretty much everybody is exposed to some amount of background radiation during their lives. When things are exposed to radiation, especially high amounts of radiation, we say that they become irradiated. So you know you cannot become radioactive just by being exposed to radiation. Things exposed to radiation are called irradiated items or things. And then finally, you can receive different doses of radiation, and that depends on time exposed and distance from the source. So if we use sun as our example of radiation, the longer you're out in the sun without any sort of sunscreen or protection, the higher a dose you're going to get, the worse of a sunburn you're going to get. Similarly, if you've ever been up in the mountains, which some of you might have, it's much easier to get a sunburn at a higher elevation than it is at a lower elevation because you're closer to the sun. So your time exposed as well as your distance from the source is what causes different doses of radiation. That's why even though we're all exposed to some amount of radiation on a regular basis, the time exposed and the distance is minimal enough that the dose is small and our bodies can handle it. So that gives a little bit of background about the history of radiation and our different types of sources and the different types of radioactive particles.